would be modes of operation suitable for computing on encrypted data. Is waar je dragers not just smart en nog geen stam, en dragers toegeefgetal.
Alright, can you hear me?
Yes.
Yeah, cool. So, I'm Dragos. This talk is going to be about modes of operations for computing on encrypted data, joint work with Nigel and Martijn. This was done at the University of Bristol. Some of them are now at K11, as you might know. Now, flash news. A multi-party computation has access this in 2018. Now, most of you may wonder how did this happen and what is MPC. So, multi-party computation allows multiple parties, such as Alice, Bob, and Charlie, to compute a function over their inputs while keeping them private. Now, what is the problem we're trying to solve? Suppose we have some institutions, like, say, 3 banks, which have a secret, a really important piece of data, which is shared, shared among them, such that if all of them add their share, they can reveal that important piece of data. Now, they want to create a long-term storage solution for these shares. So they can naively encrypt each share and put it in a database. Now, there's a more clever way to do this, namely do a long-term storage solution. And as you might have guessed, the answer is MPC. Of course, we can evaluate the encryption function using a shared key and a shared input, and in this way we get a threefold database reduction. So we save some space, but we're using MPC. Now there's something missing here. Can you guess? Well, the tag. So we need authenticated encryption in MPC because it guarantees confidentiality, integrity, and the fact that those were indeed the MPC servers who computed the encryption. And we get loads of stuff for free. For example, like if we've got these maps, we can detect malicious encryption keys, whether the servers cheated, lied about their encryption keys, we can detect that with MACs. So there was some prior work done, which was published at CCS 2016, which looked at how to evaluate PRFs in MPC. Namely, 2 of the most efficient PRFs found there were MPC, which was designed for snarks, and Legendre PRF, which is a really old PRF, but apparently it's well suitable for the MPC case. Now, they also proposed on how to do authenticated encryption, namely compute the tag, and this is done in CBC MAC style. So we've got a message block, we feed that to the encryption function. Now another message block comes in, we add that to the previous ciphertext, we feed that to the encryption function. Another message block, we add that to the previous ciphertext, we feed that again to the encryption function, and we can get the tag in this way. Now the main drawback of this is that in MPC, this is serial computation, which means that every time we're going to add a message block, the number of rounds will increase proportional to the number of message blocks. So every time we add another block, we increase the number of rounds with the number of rounds of an encryption function. So we need highly parallel authenticated encryption. So what we have done is basically we start with a secret shared input and a secret shared key, and we compute the encryption function and the tag in MPC. So we were the first to analyze authenticated encryption in MPC. Useful MPC happens in FP, in prime fields, which is why we need authenticated encryption and PRS mod P. And we also look for authenticated encryption, which is done in parallel, and we found some modes such as OTR, counter mode plus PMAC, and there's also another one which is counter mode plus HART and MAC. Okay, I have a confession to make. I love stories. I think stories are a great way to communicate your ideas. So I've done a story. For this talk, I tried to create a story. Now, the story is about choices. So you've got the blue pill, which is if you're taking, the story ends, you wake up in your bed and believe whatever you want to believe, and you take the red pill. You stay in Wonderland, I'll show you how deep the rabbit hole goes. So the hero of our story is Bob. Now, what pill do you think Bob should take? Red, exactly. So down the rabbit hole, MPC with secret sharing. In our system, namely speed, the secret sharing works this way. Basically, each party has an additive sharing of X, a random share, so that if all the parties add their share together, they obtain the secret value. So in most of the MPC protocols, you can usually split them into two phases. The preprocessing phase, where you generate triples. Namely, you have a random sharing of A, a random sharing of B, and a share of their product. So Bob doesn't really understand what generating triples mean. And the answer is, if you really drink around Belgium, there is a beer called triple. So this is a triple. Now, in MPC, a triple is not enough. So we're going to need loads of them. All right. Now, the online phase, we get to use the triples. Of course, Bob doesn't really know what using triples is. And this can be illustrated as with what happens at every round session or conference dinner. We get to use the triples, namely party. Okay, so now let's see how an MPC circuit evaluation is done. A circuit evaluation is done in MPC. So we've got some shared inputs, secret shared inputs, X, Y, and Z, and we've got the parties with their inputs. Now, if we want to multiply X and Y, Y and Z, we're going to use some triples. So that means those parties will communicate in order to perform those multiplications. Now, addition comes for free. It can be done locally, so that's cheap in MPC. Now, another multiplication comes in. We're going to use another triple. Parties will communicate again. So in total, we have to use 3 triples and 2 communication rounds. So the main takeaway from here is that linear operations are for free, mostly, and multiplications are the expensive part of the protocol. Now, remember the story? We've got the blue pill and the red pill. Now, in our setting, blue means public, and red means secret. And in MPC, there is a way to convert from secret to public, namely through an operation called reveal. So now let's take some examples. So we've got the first 2 columns, which take public input, feed that to a tweakable encryption function, and we get the public ciphertext and the secret ciphertext. Now the last 2 columns, we have 2 secret messages. We feed those to the encryption function, and we can get either a public ciphertext or a secret ciphertext. Now, to do tweakable encryption in MPC, we've looked at what tweakable encryption, what tweaks can we apply. So we found out that there was kind of none for MPC which are friendly. Namely, they are all mostly working in binary fields. So we tried something in prime fields because that's how our inputs are in prime fields. So this tweakable encryption, so we've designed this MPC-friendly tweak such that you take a nonce, you feed it to the encryption function, then you multiply by a counter, you add the message, and then run that for the encryption function call again. So now, let's compute PMAC using that tweakable encryption. So we've got some public messages. We feed those in our tweakable encryption. We sum those ciphertext we add the last block and then feed that again in the encryption function, in the typical encryption. So we get the tag. Now you may wonder, why are the messages public? Well, why are the messages public? Well, if we're going to do AE with counter mode plus PMAC, we have an nonce, right? We get that feed in the typical encryption calls. We get some ciphertext. We add our secret messages, and then we get some ciphertext. Now, because ciphertext can be public, right? We can simply apply the reveal operation, and then we'll get from secret ciphertext to public ciphertext. And that is important because our encryption calls can be optimized if we have public input. So now, from those ciphertext, we apply PMAC and get the tag. Cool. So now we try to benchmark these. And of course, we are thinking that everything will go as planned and the bullets will stop. But in reality, we end up with this. Unfortunately, ideal is always not the case where it's also real. So when we benchmark these, let's say for PMAC, counter mode plus PMAC, and we instantiate that with the Legendre PRF and MPC PRF, we notice that the latency, every time we double the number of message blocks, the latency doubles for the Legendre. Whereas for MPC, we get almost constant latency. Now why that happens? I tried to think of a way to explain that last night, and I realized that the best way is to do it with an analogy. So suppose we have a gardener. No. We have a beer tap, right? So we have a beer tap, and the beer is pouring. Now, because we have a glass and we just get one drop. Now we can drink that one drop, and then the next drop can fall in, we can drink, next drop we can drink. So the amount of drink is the amount of beer pouring is enough for me to drink it and then place my glass and then fill that again. Now, because we're at FSE, the drink is going to pour like really fast, so we need to put a cork on that, stop the network for a while, and then drink that beer again, and then take that cork off, and then pour beer again. So the thing is that there's lots of stuff over the network. There's lots of stuff sent over the network for the Legendre symbol, and there's not enough time to compute on that. So we need to stall a bit the network in order to compute on what we have received in the previous round. Okay, so other competitive modes. So we instantiated all the modes with Legendre and MPC, and this table says like the type of mode, the number of communication rounds using the encryption or the decryption, like where we create a MAC or we check a MAC. Like on a piece of paper that looks like almost identically because it's counter mode, but in reality, if we're going to play with the shared inputs or the clear inputs, we're going to get different communication rounds for the encryption. We're going to get different circuits for encryption and decryption. So, for the most competitive one was counter mode plus #10 MAC, which can be done in MPC using 5 rounds for authenticated message, or 4 rounds for checking attack. So, some open problems. We see that preprocessing scales linearly in terms of the number of message blocks. Namely, if I add a message block, then if I double the number of message blocks, then I also double the amount of preprocessing need, which is the number of triples, as we discussed. Maybe we can create a PRF which will increase the number of rounds, but can process more messages at the same time. Also, I think there's a misunderstanding between the MPC community and the symmetric key community, like the number of rounds for a cipher is not necessarily equal to the multiplicative depth for the multi-part computation protocol. So I think we need to fix that in some way. If you have any ideas, then just come and talk to me. In any case, thank you.
Okay, in total we have 10 minutes for questions.
So I was going to ask, the thing that you showed there at the end, you showed that hashed and MAC was the fastest. Are you hashing the ciphertext so that you can do computations on stuff that's already been output that doesn't need multi-party computation?
Exactly. That's the key. So we reveal the ciphertext and the hash can be applied in here.
Okay, and then you only have to do the MPC on just the hash value, which is fine.
Yeah.
Okay,
yeah.
Thanks.
Other questions? So I have one question actually. How does, if you take an authenticated encryption scheme that uses universal encrypted or like OCB,
so first we also looked at OCB and we realized that there you need the inverse of the encryption function, and that was not that well studied in MPC. Like always the decryption function is much less efficient than the forward encryption. So there wasn't that much work done into how to evaluate the inverse of a PRF in MPC, the inverse of a block cipher in MPC.
Okay. So if there are no other questions, let's thank Dragos and all other speakers of the session again.